this. Let's go through some announcements. I'm making an additional reading assignment. This is so you can read ahead on some of the things we're going to lecture about. I've been starting to talk about indexes, and there's sections 8.3 and 8.4 in the book. Good thing to read. There's a section that talks about basically the architecture of a SQL Server type of DBMS, and that's in sections 9.1.9.4. Nothing there that should strike you as too strange. And then the area that we're going to get into very soon are the data structures underneath indexes, particularly B trees, but there's also a section on hash tables, and we've already, I don't think we've talked about them quite yet too much, but we will. Anyway, that's sections 14.1 through 14.3. Homework 2 is graded. I think there's 1 or 2 auto-grader glitches that are still being worked out, but we expect that to be resolved, and the homework grades released sometime later today, tonight. Let me remind you that when you're submitting homeworks, to follow the directions, look at the submission requirements. In particular, if it's SQL that's being requested, those are basically SQL script files. Save them with a .sql extension, please. If you don't, the GradeScope doesn't treat them correctly when it's trying to run our autograder. And submit those files directly to GradeScope, not the folder that the file is in. Again, GradeScope is fussy about this, and it'll not find the file, can't do anything with the folder, that type of thing. GradeScope expects a file. Homework 3, I guess, is due Friday. Am I correct on that? I think so. Homework 4 will be released next Monday. It'll be practicing on UML, and for this one, it'll be an individual assignment. It's not going to do any good for you to do this in a team. The idea is for you to get some practice in UML, and so no teams on this one. Homework 5 will probably be the same, so no teams. I hope teams are working well. Certainly provide us with some feedback if you think they are or they aren't. But the next 2 assignments are not really teamwork. Okay. When I'm going over your questions on ED, or going through the questions that I get asked at the end of class, then looking over the notes for the next time, I'm always thinking about, well, where are they going to get confused with this stuff? And this strikes me as an area that is just waiting to be confusing. And it's very funny. If you have your textbook with you, you can take a look at a note that's on the top of page 620 in Molina, and it basically is a response probably to, I mean, these guys teach many more years of this course than me, of the confusion that this overloaded term, we're using it constantly, and it's very hard to even give a crisp definition of it. But we who use the term know precisely what we mean by it, but it's very hard to define. And in fact, what makes it extra hard is that it's used in lots and lots of ways. I actually show 4 ways. Molina shows 3. The last one is mine, but sometimes we use the term key to mean the primary key of a relation. I've already used it frequently when we have a sort key, and that's a traditional use in data processing. That it's when the order by field X is the key there, or it can be multiple keys. We use it in terms like when we have a search key. So the field X there is whatever value we're asking for, greater than, less than. And particularly, of course, where the search key itself is one of the attributes that's used to create an index. So all of those definitions of key are valid, and they all relatively mean the same thing. Melina is kind of funny on the subject. He says in many cases, the three kinds of keys are one and the same. And if you look at the 1, 2, 3 up there, that doesn't seem possible. These are not the same things, but I guess they are in a way. Anyway, this is something that's just bound to engender confusion. I'm sorry, we use the term. We know precisely what we mean by it. We mean some kind of identification that's usually unique or unique to a tuple or things of that. That's a key. We're going to get into things like super keys, hopefully in this lecture, I think. And it's like, well, I don't even know what a key is, man. Don't start telling me about super keys. They're the keys. They're the keys. They're the keys to the kingdom here in relational databases. Okay, well, some thoughts about that. Let me slip over to a demo, back to our demo from the other day, which I hope you enjoyed. Oops, I got to get it over here. All right. So what we, let me show you, I seem to be disconnected at the moment. So let's get connected. Okay. So what we were doing before was showing you a query similar to the kinds of queries that you're doing in your homework. Here selecting the flight ID and the day of the week and the carriers, the name of the carrier. I'm doing a join to get day of the week and the name of the character from the weekdays and the carriers. So these are equal joins. And then I've got additional search criterion in my where clause, where I'm looking at flights that originate in New York and end in Los Angeles. And I use this like predicate, which is like. You don't have to specify out for a text string the exact string. You can just basically specify using a regular expression approximately, what the string is and what you expect it to be. In this case, there's a percent sign here. That's the wildcard, and basically says match up to New York, and we're good. That's considered a match. And same thing here. So that's frequently done. It makes your queries run a lot easier. One of the problems with this data set is that these values are quoted for some reason. That's a little bit of a mistake, but nobody's fixing it for you. Okay, so and we're getting generated report, which we're sorting by name, by price, by day of the week. And what we talked about before was not only going to execute this thing, but we're going to click on a button up here that says include the actual execution plan. And so you can get the plan inside this tool. You can get the plan in other tools. You can also do show plan. I believe it's the set show plan or something like that. There is it's go out on ED. I forget exactly what it is, but it's a way to generate the plan using, and it comes out as XML actually. That's the way it goes. But anyway, let's execute this. And here we got a nice grid of all of our, they're nicely ordered by, what do we order them by? By the carrier. So we can easily, I don't know why that's important, but apparently it is. And then we're looking at the price and then the day of the week. You could choose whatever sort sequence you want here. I'm not sure what this query is for exactly, but one of the things we wanted to do was look at the execution plan and see, well, I guess that'll fit. That's pretty good. And because it was doing this join, this from flights and from weekdays and from carriers, you're going to see out on the edge of the plan, the first thing that's being done is a scan, clustered index scan. It's called a scan, where they're going to go through so many rows of this particular file and this particular table, I'm sorry, is carriers. There's 1,594 entries in that row, and they're all going to be ran up to handle this query. And then we're going to have another scan also of the index. That means the primary key is what's being used to run through the file. And we haven't discussed it yet, but a clustered index, basically, the scan means that it's physically in primary key sequence. So that's when there is a clustered index, that means that that field is also a sort key on the file. We'll show you how that works when we get to B trees. So this is a scan of this file, all 1.114 rows of it. So this is a pretty hefty query. At that point, you're going to see, because this particular machine has multiple processors, there's automatically some parallelism. It's an inner join, and that's being accomplished via hash join or hash match, same thing. Then that is going to be hash matched with a scan of the day of the week. So logically, that's probably how we think this query is going to be done, nested loop type of semantics. We're reading the flights database and the carrier database, and we're mashing them together on an equijoin. And we're pulling in data from the day of the week as well. And that's what each of these leaf nodes on this tree, this plan, which is structured as a tree, indicate. That a clustered index, a clustered index, a clustered index. So we're reading the entire table, and we're using them in their clustered sequence, which is by primary key. There's a suggestion here about creating a non-clustered index. So that is an index that, and it's going to include a number of additional fields. I'm going to ignore that for now, but the whole idea is that missing index would improve my performance of the query by, say, 70%. What I thought, because we're executing queries, and we'll go into usefulness of indexes or not, how useful fields are, I thought that, in fact, what we would, to improve this query, let's say the cardinality of this query is based on the cardinality of the number of rows that are in this particular table, which, as we saw, is over 1 million rows. So all 1 million rows are being read to execute this query. And what I would like to do is set up an index on the origin city and the destination city, on the assumption that this is the way my database here about flights is frequently going to be used. So they're going to query on what the origin, this origin city is, or what the destination city is, or both, as in this query. That's going to be frequent. Find out what flights are available between two cities. Let's set up these indexes for that. So this is the index that we wanted to add. And now this is something that takes a while, because not only does the flights database flights table have to be read, it has to, and every value, actually, it'll tell you that when you look at the execution plan, it'll tell you that it's reading all 141.114 million rows. It's sorting them, and it's creating the index itself. And it's doing that for both fields. And yeah, that's 99% of the work involved in the execution of this statement is reading through that file. Now, though, the benefit of once we have the index, where we got clearly we did some work there, so hopefully we get some benefit out of it. There we go. And let's go back and re-execute the query that we did before. It comes back also pretty quickly. It's probably cached at this point. And this is what I focused on last time, which is what was the difference in the result of the query now that I have these indexes. And now the leaf nodes here show a clustered index lookup, and you'll see that the bottom, it calls it a seek key, and it's going to look at the origin city, and it's going to look for only, if you see the seek predicates, for those values in the index that have New York in them. And there's an estimate here that those are 2,000 rows that are going to be read from the database, not 1.114 million. And it's also going to look at the second index. The second part is an index seek, where the predicate is going to look at Los Angeles against the destination city, and there's an estimate of about 40,000 rows. So instead of reading with this index, which had to create the index, I had to read through the entire flights database at one time for each index. But now that I have it, I'm going to make those this kind of a query run considerably faster, reducing by over 1 million rows that I don't no longer have to read because I have this index. This index just allows the database to return the number of rows very quickly, in this case about 40,000. After that, you've got some other things going on like a hash match. Here we're actually getting the data. Once we have these particular fields, these records, and we join them up, we're eventually going to need more data out of the flights database, but that can be a key lookup. That could be just the rows that result in the query, and it's telling me that's about 2,000 rows. And there'll be a message here that'll actually show you the length of the result set, which you can verify by scrolling through here. So that's how that execution plan works. You benefiting it from taking the advantage of those two indexes. Okay, so we've seen that before. Let's go on and see something a little newer, which is, the thing that I wanted to show you here was, a point to be made. So let's go look at our flights. I better refresh this because I've done some stuff. And let's refresh the flights table. And now we can see the columns. But now we see the primary key, we see the foreign key, we see the foreign key. Those kind of foreign keys have been put into the application and put into the tables by the database administrator, the database designer, which is what we're going to get into today, purely for the purpose of saving space in the database. They're not all that, well, the carrier ID saves a lot of space. But the carrier ID fields, if we were to look at the carrier IDs, let's do a quick query on that. Select the top 1,000 rows. You see a whole lot of text. So instead of including that text in every flight, what's being included instead is some kind of an abbreviation for the carrier ID. So the effect is that in each flight, we don't have that text, and but we do require a lookup, a simple join against that file. If you think about it, when we're talking about these data models, this is a feature of the way this database is designed, purely designed to save space in the database, and has nothing to do with the underlying data model. What is parallelism, by the way? Parallelism is a topic we're going to get to, but we're not going to say too much about it in this particular class. But it's the idea of taking a query or taking any program and taking advantage of multiple processors on the machine to the ability to hopefully speed it up. So it's a popular speed up technique that takes advantage of the architectures that we have where there are multiple processors. On this particular machine, I don't remember how many processors there are, but I'm going to say you'll see that there's one socket, there's 6 cores, and there's 12 logical processors. And if I don't want to go into what all that means, but it basically has 6 dedicated pieces of hardware, each of which becomes 2 logical processors, 2 physical, looks like 2 physical processors for the software, which is the operating system. The operating system thinks it has 12 threads that it can schedule simultaneously to use up others' operators. So SQL Server is sitting here thinking, well, the SQL Server is expecting that it owns the entire hardware. It owns the hardware. It typically is deployed on dedicated machines. They might be virtual machines or they might be physical machines, but it typically is deployed as those are deployed as dedicated machines. In other words, it only runs one particular application. So it might as well take advantage of them. Otherwise, it's not using all the processing power that's available. Even your phones these days have about 4 processors on them, like this iPhone. I think this has 4, but not as readily accessible. The performance information about it. Performance is what I do for a real job. Okay. Can I explain what it is with in and out the index? I think not. Well, you're going to get a chance to do it. That's kind of the key thing. I'm not sure how to explain it again. The point of the index is that it is another path into the table. And in this case, a faster way in if you're searching for a field that you're indexing on the destination city or on the, it's a way of searching for those particular records directly. It's very comparable to the indexes that you see in a book, like an author index or a subject index. If you want to look, I typically like to see if say, for instance, I'm quoted. If they have an author index, I'll be able to look it up directly to see if I'm in the book, that kind of thing. So it's a direct way of doing it rather than scan through the whole book looking for my name. If somebody is kind enough to add an author index. It's a little bit of work. Somebody's got to go through the whole manuscript. I've written a couple of books. You have to go through the whole manuscript to create a subject index and kind of pull out the subject topics that you want indexed, and then maybe you can run a program that'll look for those topics. But typically the person that indexes then writes down the page where that starts or where that topic starts. That's why they're error-prone. It's a relatively error-prone process. Very analogous to what we're doing here with these data files. We're creating indexes, we're creating faster ways to look up the data. Okay, so, but in the context of what we're talking about this last week and this week, these data models, what I wanted you to understand is that this day of the week, day of the month, and particularly carrier ID, day of the week and day of the month, I think are really just, they'll try to get you to practice joins. But carrier ID has a function, which is to save room in the database. And rather than have, you put this much text in instead of this much text in for each of these airlines. Okay. We now have some keys to this file. So we have our primary key, which is the file ID, and we have the foreign key and the foreign key and the foreign key. So we knew that. Now, though, we'll also see that we have some additional indexes on the file. And here we have our file key. They just sorted them in alphabetical order here. They're not. And that's the one that's clustered. That's the one that reflects the physical sequence of the data, the rows in the table. They are sorted by file ID. And this is this is a non-unique index. It's also non-clustered. It says it's not sorted the file's not sorted that way. But if you wanted to sort the file that way, you could use this index to do it and avoid a sort. It's a pre-sorted index, just the way an author index is in pre-sorted order for you to find the authors. That's not how you'd normally read the book, but if you just want to get to those authors, you would go there first. So we've indexed at origin and we've indexed destination. All this stuff that's in this part of the app, this is the metadata associated with this particular database. And I guess I thought I would just explore that a little bit as another peek into what's going on behind the scenes. This metadata, data about your databases, data about at your table level, at your column level, what the names of the fields are, the indexing, all of that stuff is stored in the database. It's stored in a series of sys.dot tables that are accessible, and they're associated with the master database, which you might have noticed up here somewhere. What is that kind of gets installed here? That's the master, Okay, and there's a temp DB that's used for sorting. in case there's an overflow of memory, you need to sort someplace or create a very large, say a width, and a very large table that there's no place for it in memory. It's really not an issue for this size database given this machine, but that's what TempDB is used for. What the other ones do, I have no idea. So don't ask me. So there's Microsoft in it, so I guess it's some Microsoft stuff, and I have no idea what's in the model. Okay, so here we are, for instance. Let's look at how some of this metadata. Here's a select. I'm looking for a type description. I'm getting a count of the type description, and I'm getting this from the sys.objects. I'm grouping by type description, whatever that is, and I'm basically doing, oh, sorry, let's one at a time. Let's do that one. And let's execute that one. And so apparently this sys.objects is at a very high level showing you what objects are in the database. System table, stored procedures, foreign key constraints. Oh, we created 3 of them. They are objects. They are objects represented in the database. They'll have an object ID basically, and you'll be able to go look them up. We'll do that in a minute, actually, through some of them. Here, now, I particularly care about all this stuff was built not for me. Most of the stuff was not built for me. It's built for all users of the database. So I just want to look at the user tables. And these are the user tables. They have a unique object ID, and here's their name. And this is how you find them in the rest of the metadata. What we care about this is what I'm doing is I'm going to get not only the user table, but I'm going to join that to the, if you notice here, the system columns, sys.columns. And what I'm looking at to do here is to create a report that shows me by table name, and by the table name, which columns are there, how big they are, stuff like that. And I just want IDs for them. So let's execute that. So if I wanted to, I could add, well, just and table name like flights, which I'm going to do in a minute, and just look at the ones for the flights. But here's the results of that generic query. And you can see names and column names and different types and how big the columns are. So all of the information, basically this app is a GUI on top of all this data, if you will. Everything over here is actually a reflection of what's being stored for you in the database. The final thing I'm going to do is, I might do one more. Let's look at this. This is the physical structure of the flights table, the flight small table. And it basically shows that there is a clustered index. And the clustered index we'll find also includes the flight's data. So that's index number 1. And these are the 2 indexes that I just created. I keep creating them and deleting them, so somehow the numbers keep getting incremented, I guess. And those are non-clustered index. By the way, I wonder how big they are. All that stuff is. There's a query to do that. And that query is how big the table is. It's a pretty big table. It shows me that in pages. That's 25,000 pages. And just have to know SQL Server uses an 8K page. So that would give you the total size of the file at the moment. And actually, I think I have one more query to show you where I break out that 25,000 pages into the size of the main table with its clustered index and each of the indexes that I created separately. Each of the indexes I created on origin, origin city and destination city took about 4,000 pages each. So it's not trivial when the entire file, the entire table can fit in 17,000. So that's how the space nets out. Would I be tested on these system structures? No, I just thought it might be useful as you're navigating through the database to see how some of this stuff works. No, we're just trying to teach you how it works, not necessarily test you on all of it. It's all grist for the mill, however. Okay, Any other questions before I go on to the actual lecture? I just wanted to show you a little bit more, and we'll keep showing you a little bit more as we go through the class. We are now starting to transition. Well, we're talking about all this abstract stuff, data models and things like that. Now we're going to, in this lecture, start to actually say, well, how do data models get translated into database structures? That seems like a worthwhile thing because that's what we're talking about. How do we know to do this? And what is the right way, if there is a right way of doing it? So we looked at the ER diagrams. Here's this company that makes multiple products, the arrow kind of in a non-intuitive way, pointing in the opposite direction. I don't know who came up with this format, but that's what you have to learn. And we've got these tables that we're going to create now that are associated with this entity set and this entity set and foreign keys and primary keys, etc. So we've reviewed that a little bit, and you're starting to practice that in your homeworks. We call this the ER part, the entity relationship part, the conceptual model, and we call this the physical database. And what we want to look for is, well, this is the metadata. This is the data that describes how that physical database is going to be laid out. And we want to start to think about how to get there, get from the logical database to a physical database. And what we're going to look at, we've seen table definitions, column constraints, primary keys, foreign keys, and other secondary indexes. There's origin and destination indexes. There's also known as secondary indexes. They're not the primary keys, so they must be secondary. And how we wind up with the physical models that we do. We've got, and the database model that we're using, Flights, has a very limited data model. In fact, all of the auxiliary tables to the Flights database, all that data could have been stored right in the Flights database. It simply didn't store day of the week, didn't store a month, didn't store the name of the carrier to save space. And that's all. But these kind of data models, when we're looking at products and companies and purchase orders, we're not so concerned about, we're concerned about laying out a database, and we are concerned about space, and we're going to do some of that technique. Instead of storing a state name, the name of a state, we're going to store a state abbreviation. Instead of storing a product ID everywhere, a product name everywhere, we're going to have a products table that has the product name all written out and your name written out in some way, but you'll be in a customer ID. So, but this is going to present something that's a little bit more complicated that you're dealing with in the homework, but that's more of what people do when they design databases. Okay. Now, oh, that's fancy, a fancy animation. The term that's used to get from this conceptual model to the kinds of tables that are defined and the various constraints in them is normalization, in particular the table definitions and the columns that are there. That's called normalization. Don't ask me why. It was a term invented by, or first adopted by, Ted Codd, and we've used it when he first published Relational Database. The idea that people should use relational databases, everybody picks it up. And so we mean normalization. What we mean by normalization is a little bit like what we mean in a statistical routine where we want to normalize the data using a normal distribution. We want to become to some kind of standard way of dealing with it. It's not quite what normalization means in this context, and you just have to accept the term. It's kind of like key. It doesn't have a great meaning. But it's a technique for getting a logical database defined that eliminates anomalies. I think that's the key thing here. And that's what we're going to spend a few minutes on, is what anomalies occur in data models. And these are the things that we would like to design a database to avoid. We're going to look at the method for getting rid of these anomalies, and the method turns into an algorithm that people that people can use that's based on the idea of functional dependencies, another terrible term. But the algorithm itself isn't all that practical, but it will give you a sense of what it's used for. Okay, so let's take a simple example, and we're building a simple directory where we're keeping information about the names of our customers, their social security numbers, some kind of ID information, their phone numbers, and their city. And we associate people with the city they live in, and we associate people with any phone numbers they have in this model. I see nice rows and columns, so this could go right into a relational database. But we'll also see that there are issues that arise that are targeted as anomalies, because they cause your logic in doing SQL to be a little more complicated than you would like, or for most things. Actually, the trade-off is you have to join everything once you normalize it, but you get rid of these anomalies. Okay, here are three kinds of anomalies: insertion, update anomalies, and deletion anomalies. If we have a new contact, Ellie, but Ellie doesn't have a phone yet, can that be represented in this table? Well, yeah, you could have Ellie, and they have this data about Ellie, we have this data about Ellie, but we don't have a phone number. And it may very well be that this is a non-null field, and we can't even put it in the database. The anomaly related to update has to do with, say, what happens when Fred decides to move out of Seattle to the east side, so he's now in Bellevue. And the point of that is that Fred is not in a single row of the database. So there are multiple rows where the city column has to be updated. That's a little bit of an anomaly. And then we've got the deletion anomalies, and maybe this isn't the best example of it, but okay, Joe, I don't know, lost his phone, doesn't have a phone. We thought he had a phone. I don't know what happened to it, but it's time to delete Joe's phone. Can we delete Joe's phone without deleting the entire row? So that's what we have to know, that to leave this Joe row here, but just blank it out. Not just delete Joe. Don't leave Joe as a side effect of deleting his phone. And these anomalies, these things that make it a little bit more complicated, the fact that I have to update 2 rows in the database just to change a city, or whether or not I can add people to this database when they don't have some of the fields filled in, they basically arise because the schema calls for storing redundant data. Steve is there. Thank you, Steve. Do I need to stop? No. Okay, good. So, and the general way, if I look at this is pretty simple. I can break this up where, based on one-to-one relations between the name, the social security, and the city where this person lives, and the fact that this person could have 2 phones. No problem. They can't live in 2 cities at the same time, but they can have more than 1 phone. They can have as many phones as they want in this schema, and that's a good thing. If they get a new phone number, we just add the phone number. Actually, yeah, I've got 2 different phone numbers there. Okay, so logically, I know that I could break this relation in this fashion and eliminate that redundancy. And I didn't really specify how I will get the original relation. So this kind of breaking the relation is known as decomposition, and this kind of particular decomposition is lossless because I can put the original tables back together again. And we're very happy with this arrangement. We're happier because the anomalies are gone. It's easy to move Fred to Bellevue. There's just one place in the database that I have to change. It's easy to delete all of the phone numbers associated with Joe. There's one place in the database for everything. So this design makes those kind of operations very simple. Does cause us, if we ever want a report of Fred and Joe and their phone numbers, for us to determine the functional dependencies. That's the term that it's used. And there's something like keys to the rows, to the tuples. And you use the FDs, functional dependencies, to normalize the schema into a better or appropriate, I guess, I think normalization results in a better database design. So that's the process of normalization that we want to learn a little bit more about contact info. Then I've got their vehicles, and that has something to do with employee parking purchase, keeping track of making sure other people are parking in the parking spaces reserved for them. And we start with a flat table of all the employees that has all of these attributes in it: employee ID, a name, a home address, a job, a salary, a phone, a make, model, year, license, all the information about the vehicles. And this employee database looks a little bit like this. Here I have Bob. Here's Bob's home address. Here's his job. Here's his salary. Here's a phone. There are 2 entries of Bob. Apparently has 2 phones. And he's also got 2 cars. He's got a Ford Escort and he's got a Honda Civic, and here's some junk about those cars. Now, Carol, she's a director, happens to own a nice Tesla, but she has a phone. She's got 3 cars. She's got a Toyota and a VW. 3 cars, 3 entries in the employee database. And here's Jake, and Jake has got the 2 cars. He's got a Chevy Nova and he's got a Jeep Cherokee. And we've got Sue, just joined the company and making a nice salary to start. It's probably a little on the low side, but I didn't want to get anybody's hopes, expectations up too high, but doesn't have a car yet. So this is our first cut of the database. And as I said, making this a little bit more realistic is you can see that if you start looking at this database over a large company with lots and lots of employees, you're seeing a lot of redundant data. I flagged some of it. Here's redundant data about Bob. Here's redundant data about Carol. Here's redundant data about Jake. In one case, Bob's redundant data is because of multiple phone numbers and for multiple cars. In the case of Carol, it's only because of multiple cars. Whoops, this should have been extended up. She's got that Tesla. Don't forget that Tesla. And here's just marked the redundant data. I forgot what I did here. And here's Jake, and Jake is in this because, yeah, Jake's got multiple cars. So we've got people that get in because of multiple phones or multiple cars. Obviously, there is a one-to-many relation between employee and phone, and one-to-many relation between cars. And they could be no cars as well as no phones. These days, it's more likely that they have no car than they have a phone. But some of my employees don't even have a phone. They just came over on the Mayflower or something like that. Okay, so that I'm trying to give you a little bit more realistic picture of why this is a concern to people rather than that very baby picture that we looked at before. What we're going to do is how are we going to normalize that? Okay, so speaking of the redundant data, so what's wrong with that? Well, it starts to add up and increases the size of all the files, of all the tables. It also has these anomalies that makes it more difficult to update and change things. Oh, Carol got rid of this car, that old VW Golf that she was driving around. Now you have to make sure that you just eliminate this row of Carol looking for the VW and make sure that the other rows are okay. So you're kind of making it a little bit more complicated to make changes, to make additions because of those, what COD would call those anomalies. So some redundant data is helpful sometimes. I don't know, it's necessary. You wouldn't think it was necessary at all if you lived or died by normalization and used the COD rules. But sometimes it's useful to have redundant data. You just have to know that it's there. But in fact, we do have an example of foreign keys. Foreign keys are specifically there to create, they represent redundant data. They represent, oh, here's a pointer to another table. And this foreign key constraint says that data already exists. So that's a bit of redundant data right there. Now, using constraints, however, the RDBMS can manage the integrity of that duplicate data automatically. We saw that constraint at the end of the last lecture, how if you made a change to a foreign key value back at the primary key table, you could cascade that change so that it was now reflected over in the other fields that point back to it. So the duplicate data idea does waste some disk space, but that's not the principal concern raised by COD. It's these anomalies that cause that when I perform updates, when I perform deletions, I have to make sure, I have to do extra logic to make sure I'm getting the right rows out of this database. And those anomalies go away if I can figure out how to normalize it. Okay, so COD, he's the guy who that introduced these concepts, felt strongly that relational databases should be designed such that these anomalies not occur. And he came up with third normal form as a way of doing it. Third normal form is there's no redundant data in the database outside of the primary and foreign key values. So just quickly, let's see what we would do here. Oops, there's something else supposed to show up here. So what I've got here is, this is the kinds of data, as I look at this table, that is redundant when I have to add rows for phones and rows for cars. This data remains the same. This is what we say that the employee ID is a functional, these are functional dependents of the employee ID. If you know the employee ID, it's a simple matter to look up these values because they're stored in the same row of the table. So these I'm going to hold constant with, and they represent a one-to-one. They're in one-to-one relation with the employee ID. So that's the entity relationship part of it. Okay, that's where we start. Now, the employee ID, we call that a key. And these are the attributes functionally dependent on that key value. Those are the basic concepts that we're dealing with when we're talking about normalization. Now, what about the remaining attributes related to phone numbers or vehicle identification numbers? And in fact, we've got two entities there, two different entities that we want to work on. Those are 0 to n kind of relationships. A person might have no phone, or could have one phone or multiple phones, and we don't want any limit. Person might have 10 vehicles. Person collects cars. A person collects phone numbers for some reason. They could have 5 phone numbers. Okay, a little bit complicated, but there's and person. If we know the employee ID, we want to be able to associate those persons with those vehicles, those persons with the phones. So that ought to be fairly obvious what we want to do. And our normalized version of this would have the employees with just the fields related to, that are functionally dependent on employee ID, and a phones table that's just related to the phones that they have, and the cars table that's just related to the cars that they own. And that arrangement of data, I think you can see, has no duplicate data outside of primary and foreign keys. Therefore, it meets the definition of third normal form. And made it. So that's enough for today. We'll pick this up on Wednesday. What we're looking at is a couple more items about this, just some proof, and I'm not sure I'm going to try to prove it, but what we'd like to know, is there an algorithm to get from here to there? We like this design in because it's in third number form and there's no redundant data. We can do joins. This is a different kind of a join that we're seeing than in the flights database, though. These are joins that are logically related. They're equijoins, but they are based on these entity relationships, multiplicity of the entity relationships between employee and their phones and their cars. And that's a little bit how we would logically go from the conceptual model to a logical database design. Okay, I hope we're all good with that. I'll see you on Wednesday. I'm going to stop this class and move over to the other